Hi, and welcome to my lecture on Newton's Law of Cooling. Um, Today we're going to be talking about that very law. And as stated, Newton's Law of Cooling says the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding, provided that this difference is not too large. Okay. So I'm just going to define a few things. The temperature of the object is a function of time because it's cooling. And in some instances, we can consider it to be warming since it's a similar type of problem. Okay. Um, so T of T, or capital T, is the temperature of the object at time t. Little t we're going to call time, and T sub s, we're going to consider this to be a fixed constant. That's the temperature of the surrounding. So I should note that we're treating this as a constant. And I should also mention, as stated, Newton's law of cooling talks about a rate of cooling. Well, the rate of cooling is the derivative of the temperature. After all, if we have temperature, the thing that describes how that object changes is the derivative. So the derivative of temperature with respect to time is equal to or proportional to the temperature difference between the object T and its surrounding, so Ts. So that gives us this equation. Derivative of the temperature with respect to time is K times T minus Ts. Our goal is to solve for the temperature of the object, but this type of equation, this differential equation, is called a separable differential equation. And the idea is to put the temperature, put the variables together. So the rate of change of temperature goes with the variables of t. Those that describe time go with dt. Okay, so we're going to treat dt, the derivative of temperature with respect to time, as a fraction. And this leaves us to have dt over t minus t sub s is equal to k times dt. Just clearing the denominators and putting the variables together gives us that. The next thing we do is we integrate. Hey, this integral of k with respect to time, k is a constant, the variable here is time, so this is just equal to kt. To integrate t minus ts, well, we'll just do a u substitution. U is equal to t minus ts. Du dt is equal to 1 because time, or temperature, just has a derivative of 1. Ts is a constant, so everything goes away. Du is equal to dt, and this becomes this integral of 1 over u du. So now we use this key fact that this is the ln of u is equal to kt plus a constant. And now we're going to keep in mind that u is t minus t sub s is equal to kt plus a constant. To get rid of the exponential, we use its inverse. So this becomes e to the c plus kt, and this will be e to the c times by e to the kt. This is treated as another constant. Okay, so we're going to write this as td times by e to the kt, and this is t minus t sub s. Here this constant, t sub d is going to be e to the power of c, in case you're wondering where that td came from. So now we get this equation that the temperature as a function of time is Td times by e to the kt plus T sub s. T sub d turns out to be the temperature, the difference between the surrounding temperature and the initial temperature of the object. This is a function of time t, and this is Newton's law of cooling. Notice we need to figure out Td, T sub s, and K, the cooling constant of proportionality. Okay, so let's take in a little example. We're going to use this equation here. So suppose we have an object that is taken from room temperature of 72 degrees and placed into a fridge of 44 degrees. Our goal is to find the equation describing the object's temperature. We also know half an hour after the object is placed in the fridge that its temperature is 61 degrees Fahrenheit. So the first step to do is just to write out Newton's law of cooling. And here it is. The second thing that we should notice is that the temperature at the surrounding in the fridge is 44 degrees Fahrenheit. So that's 44. We need to figure out T sub d. We could just take the difference here, but let's just work it out and show that it is actually the difference. So we know that at t equals 0, the temperature is 72 degrees. Okay, so that means 72 is going to be equal to T sub d times by e to the 0, k times 0, that is, plus 44 degrees. Okay. Well, remember, e to the 0, that has a value of 1. So this says 72 is equal to T sub d plus 44. So just by subtracting 44, the temperature of the surrounding, we know that T sub d is 72 minus 44. And that will give us 28 degrees. Okay, so it really is the difference between its initial temperature and the temperature of the surrounding. So at the end of the day, you're going to say, okay, well, what do I know? Plugging in what I know, I get 28 times by e to the kt plus 44 degrees. Okay. Well, there's only one thing left to do. We need to know the value of k. Okay. So to figure out the value of k, we use that when t is equal to 30, the temperature is going to be 61 degrees. So that means 61, that's going to be equal to 28 times by e to the 30t plus 44. And now we have to solve for k. So now I have 61 minus 44. That's going to be equal to 28 times e to the 30t. Okay, so let's divide by 28. Divide by 28 there. So this equation tells us e to the 30t is going to be equal to 17 over 28. Now to solve for t, we get 30 times t is going to be this ln of 17 over 28. And so finally, excuse me, I have a little error here where I have t that should have been k. So I apologize for that, because we plugged in t equals 30, right? And k was the unknown. So that tells us k is this ln of 17 over 28. And then we divide by 30. Okay. Then this gives us approximately minus 0.016 for the value of k. So the temperature at time t is going to be given by 28 times e to the minus 0.016 times by t plus 44. Okay. Now after 60 minutes, so after 1 hour, and remember we're measuring time in 60 minutes, the temperature of this object in the fridge is just going to be T of 60 is going to be 28 times by e to the minus 0.016 times by 60 and add 44. Okay, and that's going to give us approximately 54.3 degrees Fahrenheit. Okay. One thing that you should notice is that, hey, this exponential has a negative in its exponent, so as time becomes really large, this 28 times e to the minus 0.016t becomes close to 0, and the object becomes essentially the temperature of the object in the fridge of 44 degrees. Okay. Thank you very much. See you at the next lecture.